a system for that category. So, if I want a system going to up to 600 kilometers with an attenuation category of 4 dB working in the first window on the fiber 652, the application code exists for 10 gigabit per second, which means that I can buy eventually that system, but it does not exist for the 40 gigabit per second. So, unless a vendor has its own product, ITU did not specify such a system. So, as you can see, the 40 gigabit per second system are reserved for the higher distance of 2 kilometers, while the 10 gigabit per second exists for every attenuation category for the 600 meters. Yes. 10G simply means that this system is able to carry a signal up to 10 gigabit per second, which means it can carry 2.5 gigabit per second as well. Normally we have 2.5, 10, 40, next 100. When we say that the class is 40, it means that it can carry any bit rate between 10 and 40. When we say 10, any bit rate between 2.5 and 10. MRZ is the type of modulation, which means that all the bit interval, when you transmit 1, is at eye level. Is there any piece of paper to clean the blackboard? No. Well, look. 1, 0, 1, 1, 1, 0. When I transmit 1, I am not going back to 0. This is non-return to 0. I do not return to 0. This is return to 0, please look. 1, 0, 1, 0, 1, 1. The signal stays high for half the bit interval, for example. It can be 60% or 40%, but it stays high for less than the entire duration of the bit time. With no return to 0, the signal stays high for the entire bit time. What's the difference? The difference is that return to 0 is less sensible to chromatic dispersion, because since chromatic dispersion will tend to broaden the pulse, if I start from a pulse which is narrow, the broadening will be not very important. If you broaden a non-return to 0 signal, this will go on the previous interval and on the second and on the following interval, and will interfere with another pulse. With return to 0, the broadening is less important, because you have half of the bit interval that you can use as a guard interval. The question is, why not to use always return to 0? The reply is very simple, because the bandwidth is the double. You have signals which are shorter. Bandwidth needed is twice the bandwidth of non-retard to 0. So there is a compromise. It depends on the use you want to do. When the chromatic dispersion is the major concern for performance evaluation, we'll use always retard to 0. 40 gigabit per second are mostly retard to 0 because otherwise the chromatic dispersion penalty will be very high. Is it clear? This is another table showing intra-office system specification for multi-channel system, which means WDM system. I know that these tables are a little bit boring, but I must explain the meaning of the table, how to interpret it. When we know the basic understanding of the table, we will go very fast through them. Well, unfortunately, the recommendation by ITU have been written in different times and many times from different people, so that the format of the tables is not always the same. Here we find a table in a slightly different format. Multi-channel system. The source is always in the third window. We can use any of the three types, the three main types of fibers. The target distance starts from 2 kilometers up to 20. It is not used for 2.5 gigabit per second per channel, and it is used for 10 gigabit per second channels non-return to 0. You can see there are 3 yes on the bottom line, and you can see, moreover, that there is the possibility to have both 16 and 32 channels. What does it mean? It means simply that if I go through recommendation 959.1 and I look for the application codes, I will find 5 different application codes. The application code for the 10 G at 16 channels, same bit rate, 32 channel, on G652 for 20 kilometers. Just one application code for the fiber G653, and 2 more application codes for the last column. I would like to know if the meaning of such a table is clear to you, because this is the most important part of the tutorial, to be able to understand what is written in an ITU recommendation. This is the complete reference for application of this kind of systems. Let me explain them into details. This is building A. This is building B. On the top row, I have a system, transmitter and receiver and transmitter on the other side, which is of the type A. Type A means that the attenuation category is the reduced one, 4 dB. The 4 dB, since this is a few hundred meters, the 4 dBs are given by the transit through the optical distribution frame, which means connectors, pieces of fiber, and is not very influenced by the length of the fiber between the distribution frames. On the same path, we have a signal coming from the other building. This is the type C. For the type C, the attenuation can be 4 or 6 dB, and you can see that it can be 4 since the attenuation is mainly given from by the optical distribution frame. 2 kilometers of fibers are only 0.8 dB, we said before. Then we have the type B, which is in the same building, but going through a photonic cross connect. It is a switching apparatus, switching system. So the attenuation for this can increase up to 6 dB. The same path is followed by a signal coming from building B. So that this is type D, and the attenuation can raise even to 16 dB due to the length and do the pass through the photonic source connect. Any possible case is reported in this drawing. Go into the second geographical area for WDM system, which is the metro axis. You are here. You are here in the metro axis. Still no optical amplifiers. Distances up to 80 kilometers, and this is an indication of the reason for which we don't use optical amplifiers. I said before coffee break that the typical application of an amplifier is after 80 kilometers. If the length is 80 kilometers or less, there is no need to use an optical amplifier. And about a multi-channel system, I can use both WDM system or CWDM system, which means dense WDM or coarse WDM. Did you learn the difference between the two? Is there anybody who like to tell me the difference between the two systems? Nobody's willing? That's very simple. It's only the distance between the lambdas. In dense WDM, the lambdas have a distance which can be 100 gigahertz or less. Of course, this is a grid, and I can use alternating lambdas, for example, and to have lambdas that are 200 gigahertz apart. But the important is the order of magnitude. 100 gigahertz in the third window are equivalent to 0.8 nanometer. The coarse wavelength, the lambda are very far apart. The normalized distance is at least 20 nanometers, which is 20 times more. What's the meaning of this difference? Why did we develop two different system classes? It was very simple, only WDM. Well, as in many other things, the difference is due mainly to cost reason. Because if I use WDM and I say that the two lambdas are 100 gigahertz apart, but can be 50 or 25 or even 12.5, the laser emission should be very stable. The laser in the transmitter has not to change its wavelength. To obtain this result, a very sophisticated electronic control circuit is to be developed, and moreover, the laser is to be cooled. You cannot leave the laser in the environmental temperature, otherwise it will go around with its wavelength, and if it can shift several nanometers, you understand that if the next lambda is 0.8 nanometer apart, it will go on another lambda. So for WDM system, we need specially developed lasers, which normally cost a lot of money. To be more clear, let's say 10,000 euros, 20,000 euros. For CWDM, we can use very cheap laser, because no laser, even if it is not cooled, can change its wavelength by 20 nanometers. So it will not go, it will never go in another region, and the cost could be as low as $100. So there is a reduction of cost of a factor of 200. So CWDM systems are in principle very cheap. However, I have to pay something. Last bullet. What I have to pay is that, of course, is if the spacing between lambdas is 20 nanometer, in the same bandwidth I can put much less channels. So while with WDM system I can put 80 channels on the same fiber, with CWDM I can put 4 channels or 8, not more. Well, let's start from CWDM application in the metro access. And all the relevant information is reported in the recommendation 695. And this recommendation enables the transverse compatibility, which again means that I can have a transmitter from vendor A and a receiver from vendor B. Applications are defined both in terms of black box approach. I know everything of the link, I don't know anything of the transmitter and receiver, or by a black link approach. I don't know anything of the link, I know all about transmitter and receiver. For the first case, the interface parameter are defined as a multi-channel interface, which means that I specify the wavelength to be used, and for each wavelength the parameters, which in general are the same for each wavelength, but I specify the wavelength. In the second case, I specify only one wavelength for the single channel and the parameters for that channel. The applications are specified both in terms of linear and ring structures and as unidirectional or bidirectional application. Bidirectional simply means that I have transmission on the same fiber in the two directions. So I use just one fiber to send information from both ends. If they are spaced apart, they do not interfere at all, of course. This is the reference points for a unidirectional ring with the black link approach. All that is inside this box is not known. It means that this is only a reference design with 4 optical add and drop multiplexers, but they can be 3 or 5 or 7. I can have other components and so on. What I specify are the values of the parameters here at these interfaces. Again, S stays for sending interface, R for receiving interface. The small s indicates that is a single channel link. As we saw at the very beginning of the section, there are no amplifier in this kind of application, and as target distances are concerned, we can go from 20 kilometers to 80 kilometers. 90 is a mistake. The maximum number of channels can be 16 with the channel spacing of 20 nanometer. It simply means that the channels are allocated everywhere, because 16 times 20 is 320 nanometers. The channels are allocated everywhere from the second to the third window. They go from 1300 up to 1600 nanometers. The bit rate for any single channel is 1.25 or 2.5 gigabit per second, no return to zero. 1.25 gigabit per second is an emerging bit rate which was not included in the SDH hierarchy. The SDH had 622 and the following level was 2.5. 1.25 is the bit rate corresponding to the gigabit Ethernet. The gigabit Ethernet has a nominal bit rate of 1 gigabit per second, but due to the code, which is 8B, 10B, the line speed is 1.25 gigabit per second. So this kind of system can accommodate also gigabit Ethernet. For the OADM, for the optical add-drop multiplex, we have exactly the same problem we had before lunch break with the amplifier. OADM is a noisy device because I try to drop the wavelength, but part of the wavelength will pass through because inside I have a splitter which try to route in a different direction the wavelength, but part will pass through and will be added to the new wavelength I am adding with a new signal. So this is interference, this is noise. So we have some parameters to consider which are dealing both with loss and with noise. I have insertion losses because on the pass-through system I will have a loss which is due not to the fiber or to the link, but is due to OADM. This is true both for multiplexer and demultiplexer. And it will depend also on the number of connectors and on the number of splices which are along the line. The term express OADM simply means an OADM in which there is no add or dropping of wavelength. So, of course, the OADM can be expressed from one wavelength, but not expressed from another one. So, the optical path, which is defined between the interfaces S sub S and R sub S, includes any fiber and all the other network elements, which are in the link. This will give us an attenuation class, which means that for a given application, I will have a minimum attenuation and a maximum attenuation. And moreover, I will get also a parameter for the chromatic dispersion. This simply means that I will need different application codes for different values of the parameters. I will insist on the application code. The application code is a unique identifier given by the ITU recommendation that establish that a system belongs to a given category. So when you publish a document for bid for tenders, you could specify that the system we intend to buy must be compliant with ITUT recommendation G.XXX, application code XXX, YYY, ZZZ, and so on. This is the well-known table nowadays regarding the application codes. CWDM optical system for metro access network, 4-channel unidirectional. Can be short haul or long haul, where short means the length that we saw before. The fiber can be any one of the three main fibers. And for 4-channel unidirectional application, we have application codes for 2.5 gigabit per second for any possibility. So we have 6 different application codes, but the table continues So we have also 4-channel bidirectional and 8-channel bidirectional for use both in the short haul and long haul. And as you can see, the situation is very clear for any combination. We have yes if the specification exists and we can buy that system. We have a dash if the system has not been specified. Of course, you can understand that the possible combination are many and many, so that ITU has not possibility and really is not very worthwhile to define everything. Only the most important applications are specified. This is the table containing application codes for 12-channel unidirectional and 16-channel unidirectional, same type of fibers, short haul, long haul, and you can see that does exist also a long haul application, 12-channel for 1.25 gigabit per second, which means gigabit Ethernet. Since this is an important point, I rather prefer to stop here and to resume just after lunch. At what time shall we? 2 o'clock, okay? We'll explain better this concept, which is the basis to understand this slide. We said that a maximum number of amplifiers can be traversed without affecting by noise the signal. Now, let's say there is a link which goes through 3 amplifiers, 1 optical add-drop multiplexer, 3 other amplifiers. This is the maximum number of analog devices that can be tolerated inside the link. Now, suppose the second branch of the link, the last one, has a fault. So we have to reroute the signal, dropping the wavelength and sending the wavelength in another direction. If on the new direction there are 5 amplifiers instead of 3, the total number of amplifiers plus the optical add-drop multiplexer will exceed the maximum allowed number. This means that the error probability will increase from 10 to minus 12, for example, to 10 to minus 7, which is too low. So, what are we going to do? Well, the answer is very simple. To put it into action is a little bit less simple. The answer is we can, in a given network, evaluate all the impairments, all the signal degradation introduced by the various link, and before switching, before rerouting, we could check if the new values for the degradation are compatible with the required bit error probability. This can be made either manually by the operator, which is in charge of rerouting the signal to get to recover from the fault, or automatically by a supervision system which evaluate the new path and evaluate if the degradation factor is still below the threshold for that kind of system. To put it into practice is difficult because the degradation is not a fixed value. The degradation can be established at the beginning of the link, I mean decommissioning. When we install the link, we can write in a database, one can store in the database what is the degradation factor which is expected by that link. But during the life of the system, the degradation of the link will eventually increase because optical amplifiers are amplifying less. The gain is decreasing because there was a repair in the fiber, and now the fiber is longer than it used to be at the beginning, and so on. So we know the way, but the way is difficult to follow. In this case, we see a number of optical add and drop multiplexer. In this case, the evaluation is very simple because we have 4 cascaded optical add and drop multiplexer. We just evaluate the maximum degradation, which is the degradation we get when we traverse all the optical add and drop multiplexer. This means that we can rearrange all the path. For example, we can drop the wavelength here and we have this one going through, but the degradation has been calculated, has been evaluated at the beginning. The situation is a little bit more complicated when the topology becomes more complex. In this case, we have a ring with lambdas going around the ring, and the path can be rearranged in order to get the traffic matrix we want. Moreover, the trend is from evaluation of degradation factors towards measurement of degradation factors. What does it mean? It means simply that in the network, we will not have only transmitting and switching equipment, but we will also have monitoring equipment. For example, we can put a measurement equipment here, and we can establish what is the quality factor, the Q factor of the actual wavelength, of that wavelength at the exit of that optical add and drop multiplexing. It is obvious that this will increase the complexity of the network, and this will increase the cost of the network because besides transmitting and switching signals, we have also to monitor them. We have just finished with the course wavelength division multiplexing system in the metro access networks. Now we start with WDM system, dense WDM. They are recommended in 2 different recommendations. The first one, 959.1, specify the network application with a black box approach. The second one, 698.1, use the blank link approach. In this recommendation, the interface which is recommended is an interface for links without any optical amplifiers along the line. Again, we are in a geographical portion of the network which is very limited in size. It corresponds to a large city, for example, so that the diameter and the distances which are to be traversed are less than 80 kilometers, so no need for amplifiers. The systems which are recommended are both for single channel application and for multi-channel application, which means that a number of wavelengths are specified. This is a black box specification. We have on the top of the slide a multi-channel system. As you can see, we have a transmitter which has been built to be compatible with systems in other domains, in domains of other operators of other countries, same on the receiver, and the specification covers the line that is the main optical path. The two interfaces are called main path interface sending point multi-channel, multi-path interface sending point multi-channel, main optical path interface, main path interface receiving multi-channel. Same for the single channel. The application codes are given for any combination of the parameters or the fibers. The interface points are just after the transmitter in both cases. In one case, in which we have multiple channels, the transmitter is intended just after the optical multiplexer. For the single channel is the single channel transmitter. What are the parameters that are covered in the recommendation? This is a metro access application, so that the distances are above the distances covered by intra-office systems, which means are above 20 kilometers, and they reach 80 kilometers, but in the new version of the recommendation, the distances have been extended up to 160 kilometers. As far as the bit rates are concerned, we have 2.5, which is OTU1, 10 and 40 gigabit per second. The applications are single and multi-channel, and the operating windows are the both second and third window, which means that we will have sources both at 1300 and 1500 nanometers, and the fibers will be the GX.652 for the second window, and all the three fiber type for the third window. In some cases, for example, when the distance is very long for ultra-Hall links, which means 160 at least, FEC is required to reach the wanted performance. This is the first table, which is listing all the parameters for single-channel interfaces. For the short haul, which means target distance of 20 kilometers in the second window, or 40 kilometers in the third window, the application codes exist for every combination. So that in the second window, we have 2.5, 10 giga, 40 giga, over 20 kilometers, over G.652. In the third window, we have always 40 kilometers, but 2.5 gigabit per second is specified only for single mode fiber, the 652. For the other two levels, 10 and 40, the specification is given for any combination of fibers and bit rates. The second part of the table is for long haul. Second window is increased to 40 kilometers, but it lacks the highest speed. 40 gigabit per second is not specified. In the third window, we have specification for single mode fibers, 80 kilometers, for any of the three possible bit rates. On the other two types of fibers, G653 and G655, we can see that we have a specification only for the highest bit rate, 40 gigabit per second. This, of course, reflects on the choice of the fiber. We are in a situation which is not really very clear, because we know that we can use any fiber we like, but sometimes if we are going to use non-dispersion shifted fiber, we cannot have standardized low and medium bit rate systems. They are not being specified. So please, in case, check carefully which kind of system is specified for the combination, the selected combination of parameters. Very long haul is increased to 120 kilometers. The interested fibers are the single mode fibers and the dispersion shifted, and the only application code signal class is the non-retard to zero, 10 gigabit per second. Ultra long haul, 160 kilometers, any fibers, only 2.5 gigabit per second. These systems are specified for any type of fiber for the same length, for the same bit rate. We now have a look of the multi-channel interface. The structure of the table is the same, remains the same. The only difference is that one more parameter is appearing, which is the number of channels. And I check with the handbook, please, maybe I was wrong in compiling the table. The system is specified only for short haul. This is a general rule. It means simply that as the system gets more complicated, more important from a network point of view, which means a lot of channels or high distances or something like that, it is very difficult to get interworking between different vendors. So if we are going to install in a network a system with 80 channels, each one working at 40 gigabit per second, we are quite sure that we will not find a suitable recommendation for interface between different vendors. What is the way to be followed to solve the problem? It's very simple. Imagine that you have the problem at the border with another country. You arrive with your system, 80 channels, until the border, then you split the channels into smaller number of channels, let's say 16 or 32, and you have two systems which are connected just on the border, which means 20 kilometers before and 20 kilometers after. So we get the interface at lower number of channels. Otherwise, it will be very difficult to get a working interface. Another thing that maybe you have learned speaking about components, about devices, is that lambdas can be changed. So even if I arrive with a group of 80 different lambdas and the interface systems have always the same 16, I don't know if I am clear. You arrive with 80 channels, going from channel number 0 to channel number 79. On the interface, you have only from C0 to C15. You have 16. Then you have to convert of the wavelengths to be transmitted in the group of 16 which are used for the interface. It sounds a little bit complex, but it's the only way to get interworking, effective interworking. The long-haul interface is given for the two main types of fibers. It works up to 80 kilometers on 16 channels at 2.5 gigabit per second. As I was saying before, the interface that we have just seen, defined in recommendation 959.1, are not covering any possible combination, because you can have many and many and many combinations, and it is useless to have an application code for each combination, because the vendors simply will not have in their catalog 200 different systems. They will have some tens of systems that can be equipped with different wavelengths, but by sure they will not have any systems that could eventually be specified. But during their works, the ITU members decided to follow a philosophy such that the specified application solve most of the possible interfaces problem. So there is a restricted number of interfaces, but they should be enough to solve any connection problem. This figure is not really well clear. You can see a case of a single channel interface. What I mean for single channel interface, you have a transmitter, receiver, and the interface is given on the single client transmitter. It is not clear, but you can see in the handbook. This lambda is used for ATM transmission. This lambda is used for IP transmission. This lambda is used for SDH transmission. So we have different interfaces, and different vendors can sell us the transmitters. All the rest of the network is specified as a blank link approach. So we don't know what is inside. As you can see, there are subnetworks that are different from domain to domain, from country to country, from operator to operator. So we specify the interfaces at the single channel point. What is important from this presentation we are having is that if systems which are sold by different vendors respect the same application code, they are classified according to the same application code, they will work together. They will interwork. So the only check to be done is that you are ordering and you are putting into place a system of the with the application code xxx.345.g something. If they share the same application code, they will interwork. As we saw before for the intra-office equipment, this is a complete figure which is showing all the possible interfaces that can be met inside a metro access network. Let's start from the left-hand side. We see that we are in the presence of three different administrative domains. 1, 2, 3. I repeat, they could be different countries, they could be different operators, they could be different islands inside the network of a single operator. Maybe Marconi equipment, Alcatel equipment, Huawei equipment. So same operator, but with the islands in the network set up with the equipment from different vendors.